7.2 is one of those sections where they take a lot of concepts and cram them all in. So what we've done so far, McKenna, in 7.2 is we've done anti-differentiation. And how are you guys feeling with your antiderivatives?
Being honest, I don't feel really confident, but it's doable.
It's doable, and just like previous material, you will get stronger.
Yeah, I think it's a little shaky right now, but I think it's just because we just started.
We're going to have more practice today with it anyways. But we have covered anti-differentiation, at least the beginning part of it. Now, the second thing that rises in this lesson is called differential equations. Okay? So, let's say I just have dy dx equals a constant. This is a kind of differential equation. It has a solution, and the solution to this equation is a function.
Y, right?
The solution will be y, but what will y equal? That's the question.
0?
Well, you have to anti-differentiate this, right? Dy dx. You're close.
1. No?
Dy dx equals
X plus C.
c. So Carrie said x plus c. So if I differentiate x plus c, do I get c?
No, you get 1.
You get 1.
CX.
There we go, yes. Now there's still something missing,
Plus C.
plus, and since I'm already using c, I'll say plus d.
And D is the constant.
D is another constant, yeah. So, can I convince you that if you differentiate cx plus d, you get,
Plus D.
well, the derivative of cx would be c, and the derivative of d, since d is a constant, is 0. So can I convince you that the derivative of cx plus d is c?
Yes.
Yes. This is one kind of differential equation, one type, okay? Now, if I had an additional condition, I knew that y of 0 was 3. This is called an initial value problem. An initial value problem. Because now I have a condition that I know that I didn't know before. Now, let me take this equation right here, and I'm going to say dy dx equals 2. Okay. What is the solution to that equation, that differential equation? 2x
Plus
plus, we'll say capital C, because in this case, are we using C? No. But what I'm going to do now, Carrie, is I'm going to bring in the initial value. I know that y of 0 is 3. What kind of consequences does that have?
0 is 3.
Yes. Does that make sense? That's exactly right. So is there any more ambiguity about what C is? No, because I know that 2 times 0 plus C needs to be 3, since this is true. So that means that C itself has to be 3, and I now have a very specific answer to my problem. It's no longer ambiguous. So initial value problems help clear up the ambiguity when we anti-differentiate. Okay? Cool. All right. Click on that. Export as file. I wish there was a quicker way to do this. Notes 1. Did everyone get my email yesterday?
Yes.
Okay, good. Is that helpful?
Yes.
All right, let's look at another kind of differential equation. dy dx equals y. Now, what we're saying here is that the derivative of y with respect to x is the function y. So y is a function of x, and I'm going to give an initial value. I'm going to say y of 0 is equal to 2. So there's my initial value. Now, here's what we do. We're going to divide both sides by y, and so we're going to have dy dx over y equals 1. Okay. Now I'm going to anti-differentiate both sides. So I use the integral. So dy dx over y equals the forgot dx here. Needed dx, 1 dx. So I anti-differentiate both sides. Now, does anybody know, by the way, dy dx, I could use a different notation here, McKenna. Yeah, bingo. So let me just use y prime instead. This becomes y prime over y dx equals integral of 1 dx. And does anybody know what this is right here? If you don't, that's okay, because it's brand new. This is equal to the natural logarithm of what? Absolute value of y. Now, let me convince you that that's true. Before we do anything else, let me convince you that that's true. What if I took d dx of the natural logarithm of y? Y is a function of x, by the way, okay? It's going to be 1 over y, and then by the chain rule, dy dx, which is y prime, and that's what this is right here. So have I thoroughly convinced you now that this is indeed true? Okay, what's the integral of 1 dx? X plus c. So now I have to solve for y. That's the goal. How do we get rid of the natural logarithm? We e both sides. So I know that y equals e to the x plus c, but that's the same thing as e to the x times e to the c. And c is the unknown constant, right? So that means that e to the c is also a constant that's unknown in this case. So what I do is I say that since c is an unknown constant, that means that e to the c is an unknown constant. So I might as well just say that it's a constant times e to the x, because it's unknown. I might as well just say that. And now I have a solution to my equation right here. I have a solution. So let me first show you that this is indeed a solution to the equation right here. So again, what I have is I have dy dx equals y, and I'm going to use what I found, constant times e to the x, and I'm going to plug it in. Okay, what is y prime of c e to the x? C e to the x. So now I substitute c e to the x on the left, and I substitute c e to the x on the right. Is this equation true? Yeah, that's the reflexive property. This equation's always true. So now I know right here, Carrie, that this is indeed a solution to the differential equation. I go back to my initial value, y of 0 has to be 2, and that's going to help me clear up what the unknown constant has to be.
Why are we changing e to the c as a constant? Why can't we leave it like that?
Well, again, if you have e to the x plus c, right? That's e to the x,
Times e to the c.
e to the c. And c is not known. All I know is it's a constant. And since that's true, that means that e to an unknown constant is itself an unknown constant. And since that's the case, I'll just replace this with the unknown constant that we've been using from the beginning, which is capital C.
But another question is if we put 0 as x, e to the 0 power will be 1. So 1 times e to the 0 will equal 2.
C times e to the 0 will be c times 1, which will be c. If x is 0, then this becomes e to the 0 plus c, but that's just e to the c, which is an unknown constant. Let's use their initial value now. I know that y of 0 is 2, so that means that 2 equals c e to the 0 power. Correct. So 2 equals c. So now I know the unknown constant.
It's 2 e to the x.
It's 2e to the x is the solution to the initial value problem. So if you're given a differential equation with an initial value, then it's called an initial value problem. Okay? Okay. Let's take another one. This is an initial value problem. So what do I do first here? To solve for this. I anti-differentiate both sides, so I take the integral of both sides. That's exactly right. What is the antiderivative of f double prime of x dx?
Okay.
You got it. Yeah, a constant. You're right. Now, I already know from the initial value that f prime of 0 is 3.
You plug in 0.
So I plug in 0, but there is no x here, but that's okay. So if x is 0,
So c is 3.
c is 3. Oop. And I went ahead and wrote c again. That's pointless. There we go, 3. Okay, what do I do now?
Well, that means that f of x is 3x.
Okay, so now I anti-differentiate again. So that means that f of x is equal to 3x plus c.
When you plug in 0.
But now from this initial value, I know that 3 times 0 plus c must be 2. So f of x equals 3x plus 2. And there it is. That's the solution to this initial value problem. A lot of times in mathematics we like to abbreviate things. So we also sometimes call these IVPs. How are we doing? Okay. Okay, let's see here. When you integrate, for example, if you take the integral of 2x dx and you get x squared plus c, this right here is the antiderivative. So little f of x was 2x, and capital F of x, the antiderivative, was x squared plus c. Okay. Once you start graphing capital F of x, the graphs are called integral curves. The graphs themselves are called integral curves. And if you notice, I still have c here, and c is not known. Okay? So what happens here, McKenna, is it can look a lot of different ways. It could be a parabola right at the origin, like that. Right? But c could also be 1. So it could be a parabola going like this. C could also be negative 2 or 3, so it could also go like this. Okay? So this picture right here, David, represents all the integral curves for the antiderivative. So if you see the word integral curves, or the phrase integral curves, that's what you're dealing with. You're dealing with the antiderivative of the function, of the derivative, and you're graphing it, is what you're doing. Okay? Now, let's say, what am I on now? Notes 5? Let's say, I want to set this up correctly. Let's say that dy dx is equal to x. And I'm not going to anti-differentiate this. What I'm going to do is this, Carrie. I know that dy dx represents the slope. So what that means is x is the slope of y at all points of x. So what if x is equal to 1? Then what is the slope y prime? 1. That's exactly right. So I draw a y-axis, and I draw an x-axis. And what I do is, at the value of 1, I draw a mini tangent line which has a slope of 1. A mini tangent line which has a slope of 1. So it's right here. There's a slope of 1. And what I'm going to do, I would have to do that, wouldn't I? All right, let's go back. Let's fix that again. All right, so I've got my y-axis here. Got my x-axis. I've got dy dx equals x. Okay, so at x equals 1, we're agreed that the slope is 1, correct? Okay, so let me try to do this again without erasing it. So at 1, the slope of the tangent line is 1. Now, here's the thing. I don't know what the c is, the constant of integration, right? So it could be here on the x-axis, but it could also be above. It could be any of these right here. Or below, right? And so what I have here are many tangent lines that I'm drawing. Okay? What if x is equal to 0? What's the slope? 0. So that means right here, Carrie, the slope's that, or it's that, or it's that, or that. Are we okay with what I'm doing so far?
Do we have to know how to do it graphically like this?
Do you what?
Do we have to know how to do it graphically like
Yeah,
this?
because this is another topic in 7.2. Yeah. Now these are called direction fields. What if x equals -1? What is the slope? -1. So what that would look like, McKenna, is that would look like this. Okay. What if x is equal to 2? 2 is the slope. So at 2, the slope is a little bit steeper, isn't it? So it can go like this, or this. And if x is -2, then the slope is -2. And I hope you see something happening here. There's something actually happening
It
here.
makes like a curve.
Yes, it actually looks like the parabola that it's supposed to be. Do you see the parabolas emerging? Okay. This is called a direction field. This is called a direction field. Okay. A direction field is a field of many tangent lines that give the overall direction of an integral curve. A field of many tangent lines that give the overall direction of an integral curve. Now, let's just go back to what you already know about dy dx equals x. If you differentiate, or not differentiate, if you anti-differentiate both sides, what are you going to get here?
Y equals 1 over x squared.
1 over x squared?
No, 1 over 2 x squared.
1/2 x squared, right? Yeah, 1/2 x squared, that's right. That's all right. So y equals 1/2 x squared. Am I missing anything?
Let's see.
Plus c. Now you already know right here that this is a parabola. What'd you say? Right, from here, exactly. Since we already know that the antiderivative of this is a parabola, what I just did was I was able to take the equation itself, the dy dx equals x, and I was actually able to graph the integral curves without actually doing the antiderivative. So what are direction fields useful for? Direction fields help us see what the antiderivative may look like without even calculating the antiderivative itself. And that's just plain cool. I can know what the antiderivative looks like by just using the differential equation. Okay? So what we've done now is we've talked about two brand new topics. We've talked about direction fields, okay? And we've talked about initial value problems, a differential equation that comes with some initial value so that it clears up what the C is. Okay? All right. Notes 6. Beautiful. There she is. All right. And so, God bless you wherever you are today.
Praise Father, Son.